Okay, thank you. So I would like to, okay, did you see that? Okay. I would like to show an ASPERA 4. Main focus is in sensors and science, operation, analysis, tools, and archive. Indeed, science I will talk on Friday, and there are several relevant talks on Friday, so keep it short. First, team. The principal investigator institute is the Swedish Institute of Space Physics in Kiruna, or IRF. And I am the PI since 2014. Before it was Stas Barabash, from the original. Co-investigators are from 17 groups in 12 countries, so it's a big international group. Okay, this is a fundamental equation here. ASPERA 4, it's not minus. ASPERA 4 equal to an IMA, iomass analyzer, electron spectrometer, ELS, plus neutral particle imager, NPI, plus neutral particle detector, 2 sensor heads on over and a scanner, movable scanner. So this is a figure or picture, flight model, iomass analyzer, and there are this term is also called the main unit. So these two units are composing an ASPERA 4. Slightly technical schematics and explanation. Iomass analyzer IMA is a typical, typical top-hat analyzer with magnet for mass analysis. We have a two-direction analysis with a symmetric axis around one axis and the elevation scan in time. Afterward, we have an energy analysis with electrostatic analyzer, and then using a permanent magnet here to divide the mass. So we can realize an energy range 10 eV approximately to 30 kV with moderate mass resolution. Electron sensor, electron spectrometer is also a top-hat analyzer that we have one plane field of view separated into 16 channels. It's also an energy analyzer using an electrostatic, it's an electrostatic analyzer. On the other hand, there are two neutral particle sensors, sometimes called energetic neutral atom, which has energy roughly 100 eV to tens of kV. And for this, we cannot use the electrostatic type of analysis because it's not charged. So there is several reflections before getting a detector. This is an imager, neutral particle imager. A little bit more sophisticated sensor called an energetic neutral particle detector, NPD, is using a time-of-flight system. Coming ENA will hit a start surface, it is called, and produce a start signal, and fed into a stop surface that produces a stop signal. And using a time-of-flight in between, we know the velocity. So basically, using our 4 sensors, ASPERA 4 measures in a Venus plasma environment and plasma atmosphere interaction near Venus. Basically, what we aim to measure has a wide range of energy and wide range of charge state, but almost all the composition, or say the population, can be addressed with our instrument. Scientific objectives. Basically, the main interesting point of Venus plasma environment is that Venus has no intrinsic magnetic field. So they do not have any sort of dipole. So that an atmosphere or ionosphere directly interact with the solar wind. It's completely different situation from the Earth, rather close to Mars. Well, scientific goals, originally we planned to do, well, from a proposal phase, an atmospheric coupling with the solar wind, mass addition, removal, so mass transfer from atmosphere, from the solar wind and to the atmosphere or opposite, structure of induced magnetosphere and mass composition of escaping plasma, which also address the loss of water, and neutral atmosphere and plasma interaction that is more or less addressed by energetic neutral atom imagers. And comparative planetology, so it's a comparative aspect of those objectives. And later, an extended mission addressed long-term variations. Particularly, our interest is the solar cycle dependence, how, say, 11-year solar cycle affect the plasma environment of Venus, so interaction. Recently, we have started a lower ionosphere investigation, particularly characterization dynamics, using an air braking period data, which also will be discussed on Friday. In principle, most of the above objectives had been or still are ongoing to be studied. Of course, new ideas of data analysis, say science, is really welcome. To start, so I would like to explain a little bit of operations. Our data consists, our data was taken not all the time, but somewhat in a focused way due to save data volume or telemetry. Regular operation was done in 3 phases or 3 blocks. Pericenter operation on all the sensors. We basically stop a scanner to look at a specific direction. It's approximately 3 to 6 hours near pericenter. When a spacecraft go into the eclipse, say the shadow of Venus, sometimes we start scanning. So scanner will rotate so we can have a full 4-pi coverage. Apocenter operation, it's really far from the Venus. Also we we switch on all the sensors basically, and scanner fixed in order to address solar wind conditions, say upstream conditions, which is important to know the solar wind condition. Sometimes we do calibration runs and some special operations, for example, in solar wind continuous mode that we just run through 24 hours, several days, or say air braking during our air braking, we also switched on our sensor. What we have in the data product is that for us, most variable data is an account. That means that the number of particles coming to the detector. It's in principle proportional to the physical value, so-called differential flux, namely the number of particles with specific mass, energy, and direction ranges, if you express in an equation like this. So what we get is this one, count rate, or counts. It's proportional to physical quantities of differential flux here. And this mass, energy, and direction ranges are separated into sort of bins, so histogrammed. It's in a parameter like this. well, for plasma sensors, I prepared some a little bit more detailed data product here. That to show our data set is not simple. So basically, our data product for ion is a time series of 4D matrix, 4-dimensional matrix. So we have a 5-dimensional matrix in principle. It's in a mass, 2 direction, and energy and time. Yeah. Indeed, it is in a time series of 2D matrix because we fix at a specific time energy and direction, one of the directions. And every 12 seconds, we scan energy, and every 192 seconds, we scan one direction. So with this 5-dimensional data to represent in, say, 2D or 3D plots, we need some objective depending procedure, for example, collapse or say slice, cut in a certain dimensions. For example, this one is one axis is in mass, one axis is in energy. Well, to analyze data, this data product, there are several issues to be considered. First, for example, our sensor do not cover whole the 4π field of view. We have a dead angle up and down. Also, the field of view is blocked by spacecraft, which sometimes blocked a meaningful signal. Interference during high count rate, there is some, it is called a ghost counts. Sometimes if really signal count comes here, then an interference may be seen. And also, as seen here, a proton, it's in a mass and energy, but here the proton should fall into this line, but the peak is here, but most of the part is broke, so we cannot measure those parts, unfortunately. Electrons, it's a little bit simplified equation here because we do not have a mass. We do not need to measure the mass of electrons. And one direction is not addressed because of the planetary field of view. It's basically the same. Also, there are several issues about limited field of view, not much, and also operation constraint. Due to an operation constraint, not much scan operations leading a non-coverage of 4π. It's only 2D distribution. Well, one plane distribution we could address most of the time. Also, there is an unsettled performance due to a misalignment of the sensor. It was found that there are significant amount of not significant. It's an so we should calibrate. We should compensate some performance in the different directions, different energies due to an misalignment of the sensor. Nevertheless, the data, all the data, ASPERA for data product is archived now under a planetary science archive. Well, basically available product is, as said, in counts, raw counts, spectra or matrix of ions, electrons, and ENAs. And well, one note about the high-level product is that we are now ongoing work about to calculate in a moment its density and speed and temperature of the solar wind. It will be also archived in a PSA. Estimated time scale is about 1 year from now. There is one issue to be mentioned, that and the tools to read the PSA table dataset that do not exist, at least as of my knowledge. And there are no plans to implement such tools. So how to do data analysis? Basically, recommended way is just contact to me or us. There are several unofficial tools for data analysis, so say developed by each institute or each scientist. For example, Quick Look web service, or say protein software. You can download the software and dataset, or say analysis package and library. We are now under development at IRF is that called an IRF Pi. It's we're developing a new analysis environment powered by using a Python 3. It will provide an row count access to the data, high-level product access or conversion inside the library, and which is integrated with Spice. So, message here is that if you want to start some data analysis, just contact us. That's maybe the easiest way to start with. Related to this, I just want to say a little bit about data workshop. Courtesy by Dima and Yun Kui in NAOC in Beijing. We will have a data workshop in this August, this summer. It's a joint data workshop between 3 and 4. ASPERA 3 and 4, it's basically the same data set or data structure. So it's worthwhile to combine. And if I understand correctly, it's basically an invitation only, right? It's Chinese colleagues, yeah, right. But in principle, what the message here is that similar workshop can be supported. We can support it upon request if enough interest is there. Also, individual support is always good. And best way would be to stay at IRF in our institute. We have an experience of such a visit to discuss dataset science and so on. So just the message is that, contact me. Supporting language is English and Japanese, and Swedish maybe. Okay, thank you very much.